All right, so for 6.2 exponential growth and decay functions, we've got 6 boxes to talk about, and let's just dive right into it. So the first thing is understanding what exponential growth or decay functions, what they look like. So exponential growth occurs when we have a quantity that is increasing by the same factor over equal intervals of time. So what does that look like? So for example, let's say we have, we know that every 5 years, attendance at a summer musical festival is going to double. So if we sort of wanted to graph this out and look at it, if X was a 5-year period, and let's say in the first 5 years, we had 10,000 people attend, right? In the second 5-year period, we see that we've got 20,000 people that have attended. So in a time of 5 years, we have doubled our attendance. And if we do another 5 years, you can see that we would end up over here at 40,000 people. So this is an example of exponential growth because we keep multiplying by the same growth factor, in this case happens to be 2, over equal quantities of time. So that's everything you gotta know for box 1. Okay, in box 2, we're gonna learn how to read an exponential growth equation. This is the important part in understanding what it is that we're looking at. So for exponential growth functions, they're going to be in the form of this right here. They're going to be in the form of y is equal to a times 1 plus r raised to the t. A is going to be greater than 0, and your r is going to be greater than 0. And so what does all this stuff mean? So the y part on the end over here, this is just going to be the amount that we end up with. The a part that sits out in front, that is your initial amount, so whatever amount you're starting with. The 1 plus r is your growth factor, and your rate is expressed as a decimal. That's really important. And then of course, t is just time. So let's put this into context for you. If I have y is equal to 5 times 1 plus 0.02 raised to the t, let's identify everything that we're working with here. So whatever we get on this side, this is going to be our final amount. Okay, this guy right here, the 5, is going to represent our initial amount. So this is how much we're starting with. Okay, this guy right here, the 1 plus 0.02, all of that together is the growth factor. But to dive in a little bit deeper, the 0.02, that is my rate expressed as a decimal. So that's my rate expressed as a decimal, like right up here in decimal form. And of course, t is just your time, and time is usually measured in years. So now that we know how to read all of these things, let's put one into practice here. So box number 3, using an exponential growth function. So it says the inaugural attendance of an annual music festival is equal to 150,000. All right, the attendance y is increasing 8% each year. And it says what it wants us to do is write an exponential growth model that represents the attendance after t years. And then it says how many people will attend that festival in the 5th year. Go ahead and round your answer to the nearest 1,000. So let's go ahead and do this together. Okay, so we'll use blue. So for part A, we're going to start by saying, okay, y is equal to a times 1 plus r raised to the t. Since we know we're working with a growth model, we're going to set it up this way. A is our initial amount, our 150,000. So y is equal to 150,000. Okay, we're gonna have 1 plus. Now our rate says it's 8% per year, but we have to express this as a decimal. 8% as a decimal is 0.08. So I'm gonna write that in as 0.08. And then we're gonna raise this all to the power of t. So that right there represents everything we gotta do for our growth model. Now keep in mind, you could simplify this to 150,000 times 1.08 raised to the t. So all I did there was add 1 plus the 0.08, and I did that and came up with that one. So you can do that as well if you want. You don't have to though. Okay, then part B says how many people will attend the festival in the 5th year. So what we want is we're going to say, okay, we're going to use this model that we just came up with. Okay, this is going to be 1.08, and we're going to raise this to a power of 5, all right? So on your calculators, if you don't have a calculator, looks like this. Okay, let's clear all this stuff out. We are going to do, what I recommend is doing left parenthesis 1.08, and then raise this all to the fifth. Get that number in your calculator, and then finally multiply by your initial amount, which is 150,000. So that's how you do it in the calculator. Push enter, and we're getting 220,399. So something like that. So I'll say to the nearest person, 220,399 to the nearest person, right? Okay. So this is going to be approximately 229. What the heck? What was it again? 220,399. 220,399. Okay. So that's to the nearest person. And that's how you do number 3. All right, so exponential decay occurs when a quantity decreases by the same factor over equal intervals of time. So for this one, exponential decay works exactly the same way that exponential growth did, except for the only difference here is right here. Instead of adding our rate, we're going to subtract our rate from 1. So that's the only difference, right? Our A value is still bigger than 0. Our rate is going to fall somewhere between 0 and 1. So let me give you an example of what that means for this one, okay? So let's say that this was, a 5. So if I have y is equal to 5 times 1 minus 0.03, so because we have this minus sign sitting right in front of here, I know that this is going to be a decay factor. So this is going to be my decay. So the 5 represents my initial amount, okay? The 1 minus 0.03 is my decay factor. And of course, t is just time again. So exponential decay functions work exactly the same way as growth functions. The only difference is that we are subtracting from 1 instead of adding to the 1. Okay? All right. Lastly here, in box number 5, we are identifying exponential growth and decay from tables. So it says determine whether each one represents growth or decay or neither. So the way that you do this one is, first thing you want to do is you want to check and make sure that you are increasing by an equal amount. It doesn't have to be ones, but just make sure that you're increasing by an equal amount on your x's. And in this case, I happen to be. Then look at the y's and ask yourself, what do I have to multiply 270 to get to 90? And hopefully you see that you're multiplying by a third. What do I have to do to get from 90 to 30? Well, again, I'm multiplying by a third. And then lastly, from 30 to 10, I'm multiplying by a third. So as x's are increasing by 1, y is being multiplied by a third. So this table is going to represent an exponential decay function. So this is exponential decay. Because that r value, the ratio that we're working with here, is in between 0 and 1. Because we got it by, so we would be multiplying by a third. Let's take a look at part B, all right? So again, I'm starting at 0, going to 1, going to 2, going to 3, just going up by an equal amount. So far, so good. Now look at the y's. How do I go from 5 to 10? Well, I multiply by 2. How do I go from 10 to 20? Well, I multiply by 2, and then again, I'm multiplying by 2 to get from 20 to 40. So because we are multiplying by that same amount, this is going to be an exponential growth function. So as x's are increasing by 1, y is being multiplied by 2. So this represents an exponential growth function. And again, because our rate here, our r value is bigger than 1 in this case, the rate is going to be, in this case, a 2. And that's really all you got to know for 6.2. Good luck.